Time for video 2 of our notice for our new topic 2, vectors and matrices. We're on page 4 of our notice. Now you may get a bit of deja vu when going through these next pages when we talk about vector projections and vector resolutes, because I've just ripped off the pages out of our last notice when we talked about this previously in vectors. Think about two vectors here, A and B. If you think about vector B, it can be resolved into vertical and horizontal components. Its horizontal components here, that is to B, would be in line, would be parallel to vector A here. And its vertical component that B could be resolved into would be perpendicular to vector A there, angle of theta being between them. Well, we talked about things, or we did talk previously about a scalar resolute. What's that about? Imagine that I have again vectors A and B here and an angle of theta between them. If you drop a vertical down from the point of end of B down to A, vector A, you makes the point big fat A there, that point there. You think of this as being a triangle. Cos of angle theta would be adjacent over hypotenuse. So in that case, cos of theta would be adjacent, which is the length OA, over the length of vector B there, which is represented by this length of vector B, or magnitude thereof. So if I rearrange that, I would have what is called a scalar resolute. That would be norm of B cos of angle theta. So hence that is the the scalar resolute. It's a distance from O to A. But remembering that the dot product, remember the formal definition of the dot product was A dot B is norm of A, norm of B, but cos of the angle theta. Well, we just worked out that B cos theta was this scalar resolute OA. So I could rearrange that to get another version for OA, the scalar resolute. That would be the dot product of these two vectors, A and B, divided by norm of A. So we refer to that as the scalar resolute of B on A. On A is a good clue to work out what we're going to put on the bottom here. If we're talking about on A, then it's the norm of A that we want down the bottom. Now, that's what I would normally go with if I wanted to find a scalar resolute. Find the dot product of two vectors. You would be given then divided by the norm of A, B being on A. Or, if you take vector A and divide by the norm of vector A, we also know we could also get this. Well, A divided by the norm of it gives the unit vector parallel to A, which is what this here refers to. Again, here's vector A, here's the magnitude of vector A. If you divide the vector by the magnitude, you get this unit vector A in the same direction as A, but O of length 1. And still, this is dotted with vector B. So the scalar resolute B on A is either the dot product divided by A or the unit vector in the direction of A dotted with vector B, which is what we talk about in this here box. Scalar projection of vector B on A is this, the dot product divided by the magnitude of A, or this unit vector in direction of A dotted with B. Okay, what about these examples, S and T? What is the scalar resolute of S on T? Okay, well there's the clue, it says on T. So going back to what it said in the box, how do you get that? S on T, well you just take the dot product, S by T, and if it's on T, you want that over the norm of T. Okay, bit of a sidebar. What's the norm? Not T. So what's the norm of T? Well, that would be the square root of, what's T? 5i minus 12j. So that would be 5 squared minus negative 12 squared, which is 169 square root of, and the square root of 169 is 12. And the norm of S would be the square root of, now S is 3i 4j, so that would be 3 squared plus 4 squared, that would be the square root of 9 plus 16, which is 25 squared, that would be 5. Picked some nice numbers there, didn't I? And while I'm here, what about the dot product of s and t? Okay, like we said previously, that would be the I coordinates multiplied together, so that would be 3 by 5. Added to the j coordinates multiplied together, that would be 4 times I, negative 12. That's 15, and negative 48, that is negative 33. Alright, so what's the scalar resolute of s on t? That would be negative 33 divided by the norm of t, which is 13. On the other hand, in b, what's the scalar resolute of t on s? Is there a difference? Well, there is. It's still the dot product on top, and that's not going to change. But you're going to divide by, because it's on s, it's the norm of s. So that would be negative 33 like before, but this time divided by 5. We can leave it like that. Alright, so over the page, let's talk about the vector resolute. So they were the scalar resolutes. What about the vector resolutes? Well, back to this diagram. There's b, vector b, there's vector a. Now, we describe this vector as a vector that is parallel to vector a, and this one which is perpendicular to vector a. So we talked about the horizontal vector resolute and the vertical vector resolute. The horizontal vector resolute has the magnitude of OA. Okay, so this vector B there goes from just from O to the point A. It's not, sorry, to the big letter A. This, i.e., the scalar resolute and has a direction of A, i.e., this, which we know is vector A divided by its magnitude. So once again, this vector from O to A there, capital A, is what we refer to as the horizontal vector resolute. It's got the length of the scalar resolute, which we knew previously was the dot product divided by norm of A, times by a vector, a unit vector in that direction. A unit vector in the direction of A is this, which is just A, vector A divided by its magnitude. Ooh, what a mouthful. So, here we have it. So the vector resolute of B parallel to A is given by this. Dot product divided by norm of A, which gives us the scalar resolute, which we worked out previously. Scalar resolute times by this vector, which is parallel to A, but the length of it is equal to 1, or the length of the unit vector in that case is 1. So, oh yuck, isn't that awful? And again, you could write that. If you take A and divide by its magnitude, you might still get this, which is, again, vector parallel to A of unit vector length, 1, dotted with B, and then times by the norm, or rather the unit vector A again. Wow. We'll do some examples of that in a moment. Now, what about the vector resolute of B perpendicular to A? In fact, this one here. Okay, how do I get that? Well, let's just go back to plain old vectors again. I want to go get that vector. That is B perpendicular to A. What's alternative route to do that? Well, I could go this way and then that way. That would be going negative B parallel to A plus the vector B. Or if I rearrange that, that would be B minus the vector resolute parallel to A. So in summary, what would that be in the box here though? So B perpendicular to A would be vector B, minus the one that was parallel to vector A, which is the one that we worked out previously. Dot product A and B divided by normal of A times by the unit vector A, so on and so on. Let's put all that together in this example. Sorry, not that example. This one up here. Using S and T. S is 3i plus 4j. T is 5i and 12j. So, same sort of examples that we've just used previously. So let's borrow a few things from there. Firstly, the scalar resolute of T on S. Scalar resolute, again, same thing that we did before. That is the dot product S and T. It's on S, so that would be on the magnitude of S. So previously, the dot product S and T we worked out to be negative 33 over the norm of S, which we previously worked out to be 5. Okay. If the A's and B's are vectors. Okay, the vector resolute of T parallel to S, okay, given this symbol. So it's the parallel symbol means it's parallel to S, so it's in the same direction thereof. So to do that, I need the magnitude of this thing is the same as the scalar resolute, which again is this thing. Scalar resolute that, and then times that by this, the vector S divided by its norm. So we want a vector that is in this direction of S, but is a unit vector. Sorry, didn't mean to do that. Let me just go to this side. Just over here on the little sidebar, what would that be? What would that unit vector S be? That would be the vector S divided by its norm. The vector S was 3i plus 4j, and the norm of it was square root of 3 squared plus 4 squared, which is 5. So that's vector S. So putting all that together back over here, that would be negative 33 on 5. So that would be, excuse me a moment. And finally, C, the vector resolute of T perpendicular to S, we know is T minus the parallel vector, T parallel to S, which is 5i minus 12j plus the previous one that we just worked out, which is minus of negative 33 and 25, 3i plus 4j. Now we can simplify that by putting the i's and the j's together, but I might leave you to do that yourselves. So that brings us to the end of this video, which was video 2. We'll see you again on video 3. Bye.